then the final frequency we need is going to be 15 times your 3 decibel point. So if we remember, our 3 decibel point was at a frequency of about 1.2 kilohertz. So if we take 15 times that, it'll be about 20 kilohertz. Okay, so we'll see there, we'll adjust our frequency to 20 kilohertz. Okay, then we'll want to record our 3 values at the bottom, the frequency and Vmax of our input and the Vmax of our output. And then we'll also want to measure the time difference again. So we turn on our cursor to manual type X. We'll move the white cursor to the peak of our input wave, the yellow one, and we'll move our yellow cursor to the peak of our output wave, the blue one, and we'll see our delta X there is 9.60 microseconds. And once again, we see because our input is leading, we're going to record that delta X as a negative 9.60 microseconds. Okay, and then finally, with this one, we take a picture of what's shown on our oscilloscope. For this part 1 of experiment 6, what we'll need is your 3 values measured there and your time difference for all the frequencies from 1/115th of the 3 decibel all the way up to 15 times. But the only ones we need pictures for are the 3 decibel itself, the 1/115th, and the 15 times. Then that'll complete part 1 of experiment 6. Right, now we move on to part 2 of experiment 6. Now, as you recall, the purpose of the low pass. Okay.
Going in 3, 2, 1, action.
Okay, so for now, for part 2 of experiment 6, if you recall from the low pass filter in experiment 2, how that was designed is to allow the signals with a frequency below the 3 decibel point to go through mostly unchanged, while everything above the 3 decibel point faded off to 0. But for a single low-pass filter, that fall off after the 3 decibel is not always necessarily fast enough for usage. So how we can increase that drop is by cascading 2 low-pass filters together. So we'll start off with the same low-pass filter as part 1, where we've got our resistor and capacitor in series. And now we're going to add in a second one, taking the output of this first low-pass filter and using it as the input of the second one. Now I'm introducing a new resistor. So as usual, we want to measure what its exact value is using the multimeter. So just plug it into 2 voltage points. Okay, change it to the 20K setting. 1 probe on each side of the resistor. And we'll see this one is 9.98 or 97. Okay, so we're going to take note of that resistance. Now this part is particularly important. You must keep track of which your first resistor is and which your second resistor is, because we will be using them for part 3 and we don't want to mess up what that order is. Okay, and then the same goes for our second capacitor that we're introducing. You make sure to remember which is C1 and which is C2. So as I said before, we're now going to take the output of this first low-pass filter and use it as the input of our second one. So we attach R2 to where the first capacitor and resistor meet. Okay, and then we attach C2 to the output of our second resistor. Okay, and then we also need to ground that second capacitor. Okay, so now our input is channel 1 of the oscilloscope. It goes to where the red wire and the first resistor meet. And then our output is now going to be between the second resistor and the second capacitor. Okay, so as with our single low-pass filter, we first want to find the 3 decibel point for this circuit. So if we remember, for the same input voltage, we're looking for our output voltage to be roughly 4 volts. So I'm just going to decrease my frequency until my output voltage gets to 4 volts. Okay, so now this is our 3 decibel point for our cascaded passive low-pass filter. So now we're going to follow a similar procedure as part 1. We want to record what our exact frequency, our output and input voltage are. Okay, then we're going to take a picture of this too, and then we'll use our cursor function once again to get the time difference between our input and our output. Okay, so we get a delta X of 64.0 microseconds, and as usual, because our input is leading the output, we're going to record that as a negative 64 microseconds. Okay, then we want to also measure along the same type of frequencies as part 1. What I mean by that is we're going to use our calculator to calculate what 1/15th of this frequency is. Okay, and if we do that, that's going to be about 150 hertz. Okay, so once again, when we're at this frequency, you're going to record your frequency and Vmax of your input, as well as your Vmax of your output. You're going to use your cursor function to get the time difference, and then you'll take a picture of this. And then we'll increase our frequency in multiples of 3. So we started at 1/115th, we'll go to 1/12th, 1/9th, 1/6th, 1/3. Then we'll go to the other side of our 3 decibel, where we'll do 3 times, 6 times, 9 times, 12 times, and 15 times. For each of those, you're going to record your 3 values at the bottom here, your Vmaxes and your frequency, as well as your time differences. And now to demonstrate the maximum, we want 15 times our 3 decibel, which will be about, say, 23 kilohertz. So if we adjust to that, okay, then for this 15 times your 3 decibel, we're going to record our frequency and Vmax of our input, as well as the Vmax of our output. We'll take a picture of this, and then we'll use our cursor function again to determine the time separation between our input and our output. Okay, so we see here our delta X is 8.80 microseconds. Once again, because our input is leading, the yellow one, we're going to record that as a negative 8.80 microseconds. So just to revise what we want to do, we're going to start off at 1/115th of the frequency. You're going to record your values and take a picture of your oscilloscope screen and use your cursor to find the time difference. And then we'll go to 1/12th, which you'll just record your values and use your cursor to get there. And then we'll go to 1/9th, 6th, 3rd, all the way up to 12 times. For each of those, all we'll need to do is record our values, our frequency and Vmax for input and Vmax for output, and then our time difference between input and output. And then our final frequency will be 15 times the 3 decimal point. In that one, you'll need to record your values, use your cursor function to find your time difference, and take a picture. And then that'll conclude part 2 of experiment 6.
Good.
So now for the third part of experiment 6, we want to show how introducing the integrated circuit chip from experiment 5 improves the quality of the cascaded low-pass filter. Okay, so as we know, for our integrated chip, the divot at the top tells us how to assign the leg numbers, and as with all components, you want to place it such that each leg of the component has its own potential. So we accomplish that by just placing the chip over one of these gaps here. Now, the first connections we always make for a chip are its power supply. So its minimum power supply, which is pin or leg 4, what we want to do is set that to negative 10 volts. So how we get that is by going to the variable DC negative range, and we'll adjust it to give us the required negative 10 volts, which I'll show now. And then the positive power supply for our chip, which is pin 8 or leg 8, we want that to be positive 10 volts. So we get that by attaching to the positive variable DC. Okay, now to adjust that, I just want to use the Vmax for our channel 1. Okay, so we're going to take our probe for channel 1, place it on the variable DC positive here, the pink wire, and I'll adjust it down until we get our 10 volts. Okay, then we move our probe to the brown wire, which gives us our negative DC range to power the lower half of our chip. Okay, so now we want to adjust that until it's at negative 10. And now we have the correct power supply for our chip. Okay, now to build the circuit, what we want is to start with our pin 5 connection, which involves the 2 resistors. Now, as I mentioned for part 2, it's very important that you keep track of which resistor is which. Okay, so whatever you used as R2 for part 2 is what you're going to make a connection with pin 5 of our chip. Okay, and then we're going to take our R1 resistor, which we're going to connect to the one side of the resistor, the second resistor, and then to its own potential line. Okay, then what we need is our capacitor, our C1 from part 2. It's also important that we keep these two correctly assigned. Now what we want to do is use this capacitor 1 to join between the 2 resistors and pin 7 of our chip. Okay, then our next connection is we're going to use our second capacitor from part 2. Now one side is going to join the voltage line of pin 5, and then the other side is going to go to its own voltage line, which we'll then connect to ground. All right, then our next connection is we just want to use a small wire to directly connect pins 6 and 7. So you'll just place your wire, so one side connects to the pin 7 row, and the other side connects to the pin 6 row. Okay, and then finally what we need is the input for our circuit. So it's going to be an AC input as usual. We'll connect from the out points at the top of our board to our resistor 1, okay, to its input here. Now, to get our measurements, we need channel 1 to be input, which will go between the red wire and our first resistor, and the output is going to go along the voltage line of pin 7. Okay. So now, as per all the other parts of this experiment, we want our amplitude at maximum and our wave type to be sine. And the first frequency we're going to find is the 3 decibel point. So as we know, to get that, we're going to need measure our frequency of our input as well. And then we want the Vmax of our output. Okay, so I'm going to adjust my frequency until we get our output voltage of roughly 4 volts again. Okay, so now we found the 3 decibel point for this active cascaded low-pass filter. So as usual, we're going to record our exact frequency of our input as well as the maximum voltage of both our input and output. Then we bring our cursor function back in. We want our manual time type X. We'll adjust our white cursor until it's at the peak of our input, the yellow curve, and then we'll adjust our yellow cursor until it's at the peak of our output blue curve. And we'll see our delta X value is 144 microseconds. And once again, because our input is leading, we're going to record that delta X as negative 144 microseconds. Then we remove our cursor. We want to take a picture of this. And then just as with part 1, we're going to look for the same multiples of the 3 decibel frequency. So we'll start off at the lower end, taking 1/15th of the 3 decibel frequency. So that's going to be roughly 100 hertz. Okay, we'll record our values again, frequency and Vmax of our input and Vmax of our output. We'll use our cursor function to find the time difference between our input and output. And for this 1/15th of our 3 decibel, we're also going to take this picture of our oscilloscope. And then we'll just increase the frequency in multiples of 3 again. So this is 1/15th. We'll go up to 1/12th, then 1/9th, 1/6th, 1/3. Then we go to the increasing side of 3 times the 3 decibel, 6 times, 9 times, 12 times. Now for those interceding ones of 1/12th to 12 times, all you're going to need to do is record your 3 values at the bottom of the screen and use your cursor function to find the time difference. And now if we go to our maximum value of 15 times, which is roughly, I think, 18 kilohertz. Okay, so now we're at our maximum frequency, which is about 15 times our 3 decibel point. You're going to record your frequency and Vmax of your input as well as your Vmax of your output, and then we'll use our cursor function to find the time difference. So you'll see with this one, it's rather flat, so what we can do is change the scale of our input and just use best judgment to get your time difference there. And then finally, we're just going to take a picture of this, and then that'll conclude the results for part 3 of experiment 6 and concludes experiment 6 itself.